All right.
And I guess he doesn't know. Something that I love it for. And I'm relaxed. You're gonna be here. So he's actually good. Is a teacher with me?
Was great. All right. We're going to start our final unit today. Today we're talking about area between two curves. You're going to feel like a lot of this is familiar because we've been working with area to some extent. But before with definite integrals, yeah, it's basically definite integral. And remember how before I would say, is area related? Because sometimes you may get negative values. Well, now we have a distinct formula that will ensure that we're always going to get an area value, like a positive value. So, but today you're just going to basically see it's very much related to what we've been doing with chapter 4, but now we have a very specific definition for area and not have to worry about negatives. Okay, so we're really only covering 2 sections in chapter 7 because those are the only 2 sections that will be on the AP exam. So today we'll do area. Tomorrow we'll work on area some more, but work on it from a free response AP style standpoint. And then 7.2 we'll split into 3 sections. We're going to take area and we're going to extend it into volume by talking about rotation. And then more rotation called this washer method. And next week we'll finish off with cross section and then we'll start test review. Following that, we'll have teacher work days and then volume test. That we'll have a day. Well, we'll have 2 days of review before the break and 1 day of review after the break, and then test Thursday. After that, we're going to start AP review, and I'll go over this a lot more detail. But basically, we're just going to be practicing with FRQs and multiple choice and having quizzes along the way. But I'm going to be incorporating your homework grades into the quiz and test grades to help offset any potential low grades. So if you haven't been doing your homework, you definitely want to be doing it here because these are going to be worth basically quiz and test grades. Okay, so there will be a slight deduction for any late homeworks, but minimal. Okay, so basically, if you want to maximize all those points, just turn them in on the day that they're due. Okay, but we'll go over that in a lot more detail, and then we'll spend all of April doing AP review as well as having some mock AP exams, mock AP tests. Okay. And then your AP exam is the second Monday of May 8th. Okay. All right, any questions so far right now? Okay. All right, so let's go to our notes. So if we want to find the area between 2 graphs, it's basically definite integral. Okay. Now, we've basically been working this formula for a while now, but it's always been just whatever function that we've been dealing with. And we've always left out the bottom graph because it's always been the x-axis. It's always been 0. So it's always been whatever the top graph is minus 0. So maybe a graph look like this. And we'll say, oh, it's the integral from a to b of f of x dx. Now, that will tell us the area of that region. Now, what we've been leaving out is it's the top graph, which is f of x, minus the 0 graph, which is the x-axis. Okay. But now we're going to be having a bottom function that's something other than the x-axis. So we're going to be including that. So really, I just want you guys to consider that we've been doing it the whole time. We've just been leaving out the bottom graph, but now we're going to be extending that into a minus a bottom graph. So I'll just highlight the top and bottom graph, which are pretty easy to see here. The top graph is the one that is visually higher than the other. And the bottom graph is the one that's visually lower. So this is, we're also going to be flipping this around and looking at it from a right graph minus left graph perspective. But right now, we'll do the easier one first. The important thing to notice here is that everything that you see here is in terms of x. Okay, your bound is in terms of x, your graph is in terms of x, your bottom graph is in terms of x, and then we're doing everything dx, meaning that x is our independent variable. Okay. Now the equations will take on the form of y equals. Now whatever you see on the right side of that equal sign is what you insert into the graph. Okay. So again, area formula. Let's see, for this function, for this example here, we will say the definite integral from a to b. Top graph is our f of x. Bottom graph is our g of x dx. Now, sometimes it may be necessary for you to put a big parentheses around the g of x graph. And why is that, you think? Yeah, there's multiple terms sometimes inside the g of x function. We got to distribute that negative through. So just be aware of that. Now, if there's only one term for g of x, then it doesn't matter. But if there are multiple terms, we always have to make sure we distribute that negative through. Okay. Okay, so example 2, like what we've been saying before, if your bottom graph involves the x-axis, then it feels like it's not there at all. But here, my top graph is f of x. I'm working the region from a to b, and then my bottom graph is 0. So technically, it's integral from a to b. Top graph, f of x, minus x, y equals 0. We've always been leaving the 0 out because it's always been the x-axis. Let me do a related one here. Let me call this example 2b. Now, what if the graph looked like this? Okay, so now let's say the graph is completely below the x-axis. We want to set it up using definite integrals. So area is from 1 to 2. Now, what's the top graph in this instance? The top graph is actually going to be the y equals 0. See that? So the top graph, the top boundary of the shaded region is 0. The bottom boundary is my f of x. So in this case, it's going to be what? 0 minus f of x. You see how f of x is an accumulation of all negative y values. So this formula ensures that this will give us a positive number in return, even though the region is completely below the x-axis. But we just have to follow the formula, top minus bottom. Top is whatever is higher up on the y-axis, and the lower is the whatever is lower on the y-axis. Okay, so now let's look at a full example. Example 3. Okay, find the area of the region bounded by y equals x squared and y equals 2x plus 3. So y equals x squared is the parabola. Y equals 2x plus 3 is the linear. Okay, so the first thing we need to do is we need to find the points of intersection between the two graphs. Okay, because we need to find the boundary. Okay, and the boundaries are going to happen to be the intersections of these two graphs. Okay, so find the bounds. So we're going to set the two graphs equal to each other and find those intersections. So x squared equals 2x plus 3. We have a quadratic equation. What can we do here? Bring everything over to one side. Okay. Go through factoring, multiplies to be -3, adds up to be -2. What are those two numbers? -3 and +1. Right? Double check. -3x plus 1x equals -2x. Then we know that works out. Okay, solve for x. So my first boundary is -1. My second boundary is 3. So that's my A and B. That's my left to right. Okay, so area formula. The furthest left boundary that we see is -1. The furthest right boundary we see is +3. Top graph minus bottom graph. So in this case, what's the graph on top? Which one is visually higher? The linear, right? The 2x plus 3. And the one that's below is the quadratic. Okay, so this is easy enough for us to just rely on what to find the antiderivative. Power rule, right? We do power rule, and then we work in the bounds, and then whatever number in return. Now we're guaranteed to get a positive number. Okay, if we're doing this right, we'll get a positive number. Now, what if we accidentally got these two mixed up? Then we will get a what? A negative number, but I can just get to the right answer by doing what? Changing the sign, right? So if ever you accidentally mix up your bounds, or sorry, you mix up your top and bottom graph, and if you do all your math correctly, you'll still get the right numeric answer. You just realize that you're off because it's negative, so you can just flip that to a positive. Right? So if you accidentally get the order wrong, you can still catch yourself at the end because you should always get a positive number in return. You don't do the whole problem over again. You just have to change that final step. Okay, so 2x plus 3, go through power rule, 2x squared over 2. What does 3 become? 3x. X squared becomes x cubed over 3. Do some cleanup here. The 2 cancel out. Okay, what goes in first? The 3. Okay, so I have 3 squared plus 3 times 3 minus 3 cubed over 3 minus big parentheses. Then the -1 gets inserted. Okay, you'll get to use your calculator. And your area is just 32 over 3. Right now, we don't have any units defined, but we can just keep reminding ourselves this is an area value, so units squared. But if the units was specified, then you would say centimeter squared or feet squared, kilometer squared. So this I call this the vertical orientation. This is the vertical, you can imagine you're building vertical rectangles between the graphs, and you're kind of adding these infinitely thin rectangles from one end to the other. So I feel like students find this pretty familiar because we've been doing everything from this perspective. But things get a little, we need to do some adjustments if our equations are not above each other, but horizontally related to each other, if they're to the right or to the left of each other. If that happens, we have to make a complete adjustment with the equations and also the orientation that we work with. So let's go to the second page, and I think this is what we need to really practice with. This is what's going to take some time. Now, if we're dealing with functions, we're always going to do top minus bottom. But now we may be working with equations that are not functions, okay? Equations that don't pass a vertical line test, but we can still find the area between these two equations that are not functions if we make these certain adjustments. So the graph to the right here, we see y equals f of x equals f of y. That's the graph on the right. And then we also see x equals g of y. It's kind of hidden here. So x equals. That's the graph on the left. Okay. So now, what's different here is that we're not going to be adding vertical rectangles from one end to the other. Now we're stacking horizontal rectangles. Again, this is not something that we have to do by hand, but I want you to visualize it, that every rectangle that you draw is from a horizontal perspective. I just want you to, there's something that I want you to notice about this process. So if you guys can just do this for this problem here. Now, we know that this is in a right to left relationship because all these rectangles that we drew, okay, is the right endpoint of every one of these rectangles hitting the same graph. Yes, it's all hitting that pink graph, right? This f of y. Okay. Is the left rectangle, is the left endpoint of every rectangle hitting the same graph on this one? It is, right? All the left endpoint is all hitting the yellow graph. So we know that this is a nice, clean right minus left relationship. Now, if we see right minus left, everything that we put into our equations have to be in terms of y. Our bounds have to be in terms of y. Okay, so we're looking at the lowest y value to the highest y value because we're stacking these rectangles. And then our graph is also in terms of y, which means that your equations will look like x equals. So for instance, this could be, x equals y cubed, and this could be x equals y squared plus y minus 1. And you see that your equations will always take on the form of x equals on the left, but then what gets inserted into the formula is all in terms of y. Kind of backwards, right? Because these are not functions, but we still need to be able to work with these equations. Okay, so the area for this region, this diagram, is the depth integral from lowest y value, which is c, to the highest y value, which is d, and then the right graph minus left graph. The graph on the right is the f of y, and the graph on the left is the g of y. And then we say dy. So anytime we do right minus left, we have to kind of do everything with a different orientation. Everything's in terms of y instead of x. Okay, so let's look at example 4 here. Now, what relationship do you think exists between this linear graph and this parabola? This is going to be a top minus bottom or right minus left? Right minus left. Now, I want to show you why this is not a top minus bottom, okay? Because if I were to draw these imaginary vertical rectangles, is the top of my vertical rectangle hitting the same graph every time? Okay, this one it is, right? The top of every rectangle that I can imagine will hit the same graph, but is the bottom hitting the same graph all the way through? It's not, right? If I drew a rectangle here, the bottom is hitting this curve, but if I drew the rectangle here, it's hitting a different graph. Now it's doable. We can do this top minus bottom, but we will have to do what? You have to split up into 2 separate problems because the top minus bottom would be different on this side as the top minus bottom on this side, right? So it's doable, but it's not as, we have to make that adjustment. But let's practice right now with this right minus left relationship. So if we were to draw horizontal rectangles, every horizontal rectangle that I draw, no matter where it is, the right endpoint of every rectangle is hitting the line. And if I were to draw these horizontal rectangles, the left endpoint is all hitting the what? The curve, right? So we know that's consistent, right? This is a nice, clean right curve minus left curve because we don't see a sudden change with my diagram. Okay. Now, the nice thing is that these equations are already written in the form that we want, because if we want to do right minus left, we have to take the equations that take on the form of x equals, which they do, right? So there's x equals, and then everything on the right side is in terms of what? Which variable? In terms of y. That's a good sign, right? If we see x's and y's mixed in, we have to continue to make adjustments. Okay, so first thing is we need to find bounds. So we're going to go ahead and set these 2 equations equal to each other and find the highest and lowest y values of our diagram. Okay, now this feels like a more complicated equation to solve because I have a what? What makes it more complicated here? That fraction, right? So is there something I can do to maybe get rid of that fraction? To distribute everything through by 2, right? I can just get everything up to be a whole number. So let's bring everything over to one side. Factor multiplies to be -8, adds up to be -2. For the 2 numbers. Yeah, -4 and +2. Okay, solve for y equals 4 and -2. Okay, that's consistent with the graph that we see. Lowest y value is -2, highest y value is 4. So we set up our area formula. Right, no longer are we looking at the furthest left and furthest right. We're looking at the lowest and the highest, and that's -2 to 4. And then instead of doing top minus bottom, we're doing right minus left. So what's the graph on the right? Yeah, the y plus 1, right? The line is the one on the right. So y plus 1 minus big parentheses. The graph on the left is the 1/2 y squared minus 3. Okay. Again, we can just rely on what to find the antiderivative. Power rule, right? So we can combine like terms, get everything set up and ready. Power rule, upper bound minus lower bound. The only adjustment here is instead of X's, you're dealing in terms of Y, but you would treat everything the same way algebraically. Questions? Okay, now look at the example 5 here. So there's two graphs here. You got f of x, which is the curve. Okay, and then you have g of x, which is the linear. Okay, so if I wanted to create an area equation to find the area of the shaded region, what do you notice between the relationship between the curve and the line? So we can do top minus bottom, okay, because these are both functions, but what adjustment is needed? Two separate, okay. Why is that? Yeah. Right, so on the left region here, the top graph is the what? Is the which is higher up on the y-axis. So curve, right? The curve is the top and the bottom is a line, right? But what about in the second region here? The line is on top and the curve is in the bottom. So we can't rely on one formula because if we do, then it's not consistent all the way through, right? The top and the bottom flip-flops halfway through or midway through this diagram. So we're gonna have to create two separate definite intervals. Right, one to handle the left region and the other to handle the region on the right. So area equals. Okay, let's do the first region from 1 to what? 1 to 2. Top graph minus bottom graph. The top graph is the f of x minus the linear graph. But then we flip halfway through, and then the second region is from where to where? 2 to 4. Flip flops. Now my top graph is g of x. Bottom graph is f of x. So this will ensure that if we were to add the two areas together, this will give me a positive number. This will give me a positive number. If I were to add these together, it'll nothing will cancel out. It will give me a the sum of these two actual areas. Okay, let's go to, let's see if I can pick out some problems for us to try here. Let me skip to. Yeah, let's skip to page 5. Try the ones on the top here, 1, 2, and 3. Can you represent the area of the shaded region using your integral notation? Okay, how many depth integrals do we need for this first one? 2. Top minus bottom or right minus left? Top minus bottom, right? So, within each of these regions, we can clearly see that one graph is always above the other one. So top minus bottom is good. Okay, number 2, what relationship do we have? Top minus bottom or right minus left? Also top minus bottom. But what are the two functions that we have involved here? Good, f of x and 0. Again, we need 2 definite integrals. First region, what's the graph on top? 0, right? One on the bottom is the f of x. Okay, for number 3, what relationship do you think we have here? Right minus left, okay. What's the graph on the right? Yeah, you're right. Let's see, wait, it's not very clear. It's not very clear. Yeah, I'm gonna call this g of y and this f of y. Sorry, it's not very clear in the diagram. What do our bounds look like from where to where? We always start what though? Right, we always start at the bottom though, right? Bottom to top. E to C, yeah. So if it's top minus bottom, we go from left to right. If it's right minus left equation, we go from bottom to top. We want to stack these horizontal rectangles from the lowest y value to the highest y value. Typically, your right minus left will just look a little more strange to you because these equations are going to be in terms of y, which you're not going to be as familiar with, because we're used to seeing functions, y on the left and x is on the right, but everything's going to be flip-flopped. Okay, some of these graphs are hard to see or visualize, so I'll draw these graphs for you. So let's try number 5 here. So we have the y-axis and this curve, which is x equals y squared minus y cubed. We're looking at the shaded region between them. Okay, what do you think this relationship is? Top minus bottom or right minus left? Right minus left. The giveaway is that anytime you see y's kind of grouped together, or you see something strange with the y's, that's typically kind of like a giveaway that, okay, this is going to be a right minus left because this equation is a lot easier to represent as x equals than as y equals. So what we do with right minus left, if we know that's the case, we want to make sure that we have all of our equations kind of in place. Okay, so what does that look like? Well, if we're doing right minus left, make sure that you can represent both of your equations as x equals. Okay, that kind of sets up, make sure that they're in the right form, and then you're going to be picking out the equation to use on the right side of the equal sign. So we have this equation already, right? This is already given us x equals y squared minus y cubed. And then we see the other boundary, which is over here. What's the equation of this vertical line? X equals 0, right? Vertical line is x equals 0. And we can tell that if you can see x equals, that means you know you're in the right form for right minus left, and then you're going to pick out the expression on the right side of it to represent as yeah. Mhm. Well, this is a horizontal line. So horizontal line takes on the form of y equals 0. Yeah, and then the vertical line has the equation of x equals 0. Okay, so you can tell that you can imagine drawing these horizontal rectangles from bottom to top, and this is consistent, right? Every rectangle you draw, the right endpoint is hitting that curve, and every left endpoint is hitting the y-axis. Okay, so first thing we need to do after this, we have to find our boundaries. Okay, so we have to set the equations equal to each other. Okay, what can we do here? Factor out y squared, and we're left with if I factor out a y squared, 1 minus y. Okay. So we set both equals 0, y squared equals 0, that's just y equals 0. If I set 1 minus y equal to 0, I get y equals 1, right? And we can tell that the boundary is this is 0, that's a 1, and I can just set up my definite interval. Okay. Again, this is not top minus bottom, this is right minus left. What's the graph on the right side of this shaded region? What's the boundary? The y squared minus y cubed, right? That's the one that is further to the right than the vertical line. Okay, again, power rule is enough for us to get through this problem here. One third minus 1/4. Common denominator, that'll give you 1/12. All right. Yeah, let's try number 6. You got x equals y squared and x equals 4. Again, this is a what relationship? Yeah, this is a right minus left. So set up your two equations. You got x equals 4 here. You have x equals y squared. This is the perfect setup for us to do right minus left, because first your equations are nicely set up, right? They're both x equals. And then the ones the value that we want to use in the formula will be 4 and y squared. But first we need to find what? Bounds. So we can set the 4 equal to the y squared. That will help us find the lowest and highest y values, because we're stacking these horizontal rectangles, and we're finding the area of these infinitely thin rectangles from the bottom to the top. So y equals plus or minus 2. So those are our bounds. What's the graph on the right? 4, and then the one on the left is y squared. So we're only right. The x equals just shows us that we're in the correct form. But what we insert into the formula is the 4 and the y squared, right? We don't include the x equals in our formula. Right minus left. Okay, power rule will get us to our answer. Sorry. Yeah, so here my variable is in terms of y, so your bounds will insert itself into the y variable. Yeah, if it's top minus bottom, then the bounds will get inserted to the x variable. Okay, let's skip over to number 11, see if we can skip that in. So this is a great graph here. Draw the graph for you. The 2 sin x looks like this. Okay, bounds are already given to us, but let's just go ahead and convince ourselves that they do intersect at those points. We can set these equal to each other. And get them over to the same side. Add sin x, I can combine like terms. So where is sine equal to 0? Sine is equal to 0, at pi, at 2 pi, but also in the negative direction, negative pi, negative 2 pi. And so it makes sense that they do intersect at negative pi and 0. Okay, so we can set up our depth integral. This is going to be a top minus bottom or right minus left? top minus bottom. And also the giveaway is that your equations they're nice functions, right? Y equals, everything's in terms of x. You don't see y's mixed into the equation. Do some cleanup here. I think what's the integral of sine? Negative cosine, yeah. So -3 times a negative cosine. And we're going from -pi to 0. Okay, what gets inserted first? The 0, right? So I get 3 cosine of 0 minus the 3 cosine of negative pi. We know negative pi behaves the same way as pi. So cosine of 0 is cosine of 0. 1, right? Cosine of negative pi, same thing as cosine of, cosine of negative pi, same thing as cosine of pi. What's cosine of pi? -1. So 3 minus a -3 gives me 6. All right, you guys have some homework for your textbook. Okay, I'll check that tomorrow. And we'll really dig into the relationship between top and bottom and right minus left tomorrow. Okay, make sure you bring your calculators tomorrow. We're gonna need that tomorrow.
Awesome.